This video is about the Gauss-Jordan elimination method, which is very strongly related to the Gauss elimination method. So the Gauss-Jordan elimination method, here on this picture we see Gauss as well as Jordan, who kind of came up with a variant of the Gauss elimination method. Um, let's just recap the Gauss elimination method, in which we convert the system into an upper triangular form using forward elimination, and then try to solve it using back substitution. So this looks like this. Well, we have this upper triangular form of A, and we solve it back substitution, so from x3 to x1. Now Gauss-Jordan, it kind of modifies this first step a little bit. So the matrix is converted into a diagonal form, or into a reduced echelon form, which is equivalent here. And then basically, if you have it in this diagonal form, where you have ones on the diagonal, then the solution is automatically contained in the B vector, in this modified B vector that gets modified through this elimination. So looking at this, well, the different steps that should have to be taken in this Gauss-Jordan elimination method is, first we do a forward elimination to get a upper triangular matrix. We normalize the pivots and then do a backward elimination to also remove the non-zero coefficients above the diagonal. And in doing so, well, then the B vector reads the values of the solution. Let's look at the same example that we used for Gauss elimination and check how Gauss-Jordan elimination works here. So we have this linear system, which can be recast into this matrix vector product AX is equal to B, or a matrix system. And then we do forward elimination first. So we remove the zeros below the diagonal, and that is, well, if you want to see how this is done in detail, you should check the previous video. So the result of the forward elimination was this system over here, which is an upper triangular system. The next thing we do is, well, we normalize the pivots. So divide each row by its pivot element. So here we already had ones. And the last row we divided by -5 to obtain the following system. And then we can easily perform a backward elimination. So now we remove the zeros which are above the main diagonal. So that's what we do here. So to get this zero out of the way, well, we subtract row 2 from row 1. And then we have here a 0. And also in the third column, if we subtract from this row 1 4 times row 3, then this becomes a 0. And from this row, we add 3 times row 3, that becomes also a 0. And we see that immediately that the solution is contained in this B vector over here. And if you recall from the previous video, this solution was 1, 3, and 2. Now, Gauss-Jordan is basically identical to Gauss. You perform the same mathematical operations actually, because in Gauss-Jordan elimination, you convert your matrix into a diagonal form, whereas in Gauss elimination, well, we converted it to an upper triangular form and then did the back substitution. But however, if you go take a look at how this backward elimination in Gauss-Jordan, in order to convert the triangular system to a diagonal system are, well, those operations basically are the same as the operations that you do in the back substitution. So both methods are more or less equivalent. They have the same operations, they just have a slightly different interpretation of the operations. Also, the use of and the necessity for pivoting, with, for instance, to avoid 0 elements as pivot coefficients, or to use as large a pivot coefficient as possible to reduce the amount of rounding errors, also holds for Gauss-Jordan as they did for the Gauss elimination method.